You flip a light switch, the room lights up, and you think you understand what just happened. Electricity flowed through the wire and made the bulb glow. Simple, right? But here's the thing that should bother you. That's not what happened. Not really. Most people think electricity is like water flowing through a pipe. You open the valve at the switch and electrons rush through the wire from the power plant to your bulb. It's a nice picture. Very intuitive. Completely wrong. Let me tell you what's actually going on. And I warn you, it's going to sound strange. Because electricity doesn't behave the way you think it does. When you flip that switch, something does happen almost instantly. The light comes on in less than a billionth of a second. But the electrons, the actual particles, they're barely moving. They're crawling, drifting along at maybe a millimeter per second. At that speed, it would take them hours to get from the switch to the bulb. So how does the light come on instantly? Well, the wire is already full of electrons, packed full. When you close the switch, you're not sending electrons on a journey. You're creating an electric field. And that field, that disturbance in the electromagnetic field, that's what travels fast, nearly the speed of light. Think of it like a pipe full of water. If the pipe is already full and you push at one end, the water at the other end moves almost immediately. Not because the water you pushed traveled the whole length, but because the pressure wave did. You pushed one molecule, it pushed the next, and the push traveled through. That's closer to what's happening in a wire, except it's not really a push, it's a field. And this is where things get interesting. You see, when people talk about electricity, they're usually talking about two completely different things without realizing it. There's the movement of charges, which is slow, and there's the propagation of electromagnetic fields, which is fast. And most of what we call electricity, the stuff that makes modern life work, is really about the fields. Here's something nobody tells you in school. The energy doesn't flow through the wire. I'll say that again because it sounds wrong. The energy doesn't flow through the wire. The energy flows through the space around the wire, through the electromagnetic field in the empty space surrounding the conductor. The wire is just there to guide the field, to shape it. The electrons in the wire jiggle back and forth, and that jiggling creates fields in the space outside, and those fields carry the energy. The wire itself is almost irrelevant except as a guide for where the energy should go. This isn't some theoretical curiosity. This is how it actually works. And we know this because we can calculate exactly where the energy flows using something called the Poynting vector. And when you do the math, you find that the energy is flowing in the space around the wire, not in the wire itself. Now you might think, well, that's just a mathematical trick, just a different way of describing the same thing. But no, there are experiments where this matters, where you can't understand what's happening unless you know the energy is in the fields. Take a simple circuit, a battery, a wire, a light bulb. You close the switch and the bulb lights up. Where does the energy come from? You probably think it comes from the battery, travels through the wire, and gets delivered to the bulb. Seems obvious. But watch this. The energy from the battery doesn't go through the wire to the bulb. It goes through the space between the wires. The electric field points from one wire to the other. The magnetic field wraps around the wires. And the energy flows perpendicular to both, which means it's flowing through the air in the space around and between the conductors. The battery creates the fields. The fields carry the energy through space. The bulb absorbs the energy from the fields. The wire is just the boundary condition. It's just there to tell the fields where to go. This is genuinely strange when you first encounter it. We build these elaborate copper highways for electricity, and the energy doesn't even use the highway. It flows through the empty space next to it. And here's another misconception. People think direct current means the electrons flow in one direction, and alternating current means they flow back and forth. That's true as far as it goes, but it misses the point entirely. In AC power, the electrons in your house wiring are just vibrating. 50 or 60 times per second, depending on where you live. They jiggle forward and backward about a millionth of a meter. They're not going anywhere. They're just shaking. But the energy is flowing just fine, because again, the energy is in the fields, not in the motion of the electrons. The electrons jiggle, and that jiggling creates oscillating electromagnetic fields, and those fields carry energy at the speed of light from the power plant to your appliances. You could replace all the electrons with different electrons, And as long as they jiggled the same way, nothing would change. The electrons themselves are interchangeable. What matters is the field configuration they create. Now let me tell you about something that confused people for decades: resistance. Everybody learns Ohm's law. Voltage equals current times resistance. You can calculate everything with it. But what is resistance, really? Most people think resistance is like friction. The electrons are trying to flow through the wire, and they bump into atoms, and that bumping slows them down and generates heat. And that's sort of true at a superficial level, but it's not the right way to think about it. Because remember, the electrons are barely moving anyway. They're drifting very slowly, and the drift velocity doesn't determine the current. What determines the current is how many electrons move past a point per second, and that depends on the density of free electrons and how easily they can respond to the electric field. In a good conductor like copper, there are lots of free electrons. They're not bound to any particular atom. They're just floating around in there, shared by all the atoms, part of what we call the electron sea. When you apply an electric field, all those electrons respond. They all start drifting together. Lots of electrons moving means lots of current. In a poor conductor, an insulator like rubber, the electrons are stuck. They're bound to their atoms. When you apply a field, they can stretch a little bit, shift their orbit slightly, but they can't leave. No free electrons means no current. And the resistance, the thing we measure in ohms, that's really a measure of how many electrons are free to move and how much they get scattered by imperfections in the material. Every time an electron scatters, it absorbs energy from the field and then re-radiates it in a random direction. The organized flow of energy gets converted into random thermal motion. That's heating. That's what we call resistive loss. But here's what's strange. That scattering, that interaction between the moving electrons and the atoms in the lattice, it happens because of the electromagnetic field created by all those charges. The electron isn't a little ball bouncing off atoms like billiard balls. It's a quantum mechanical wave function interacting with other quantum mechanical wave functions through electromagnetic fields. When you touch a hot wire, when you feel that heat, you're feeling the result of countless quantum mechanical interactions, electrons exchanging virtual photons with atoms, electromagnetic fields fluctuating and transferring energy. All of that just so you can have a warm wire. And nobody thinks about any of this when they plug in a toaster. Here's another thing that bothers me. People talk about voltage like it's a thing that exists at a point. This wire is at 120 volts, but voltage isn't like that. Voltage is always a difference. It's the difference in electrical potential between 2 points. Asking what the voltage is at a single point is like asking how tall you are without specifying what you're measuring from. Height above what? Sea level, the floor, the center of the earth? You need a reference. Same with voltage. When someone says a wire is at 120 volts, they mean 120 volts relative to ground, relative to the earth, which we've decided by convention to call 0 volts. But there's nothing special about the earth electrically. It's just a convenient reference point because it's big and we're all standing on it. You could pick any point in a circuit and call it 0 volts. Everything else would be measured relative to that. The physics doesn't care. The actual behavior of the circuit depends only on voltage differences, not on absolute values. And this seems like a trivial point, but it's not, because it reveals something deep about how electricity works. Electric fields don't come from voltage. They come from changes in voltage, from gradients. An electric field is just the spatial derivative of the voltage. It points in the direction voltage is decreasing, and its strength is how fast the voltage is changing. No gradient, no field, no force on charges, no force, no current. Everything depends on differences, not on absolute values. And here's where it gets really interesting. Magnetic fields work the same way, except it's changes in time instead of changes in space. When current changes, when the flow of charge accelerates, it creates a changing magnetic field. And a changing magnetic field creates an electric field, even in empty space, even with no charges around. This is what Maxwell discovered. Electric fields and magnetic fields aren't separate things. They're two aspects of the same thing, the electromagnetic field. And this field can sustain itself. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. They take turns creating each other, and the whole pattern propagates through space. That's a wave, an electromagnetic wave. And depending on how fast the fields are oscillating, we give it different names: radio waves, microwaves, infrared, light, ultraviolet, X-rays, gamma rays, all the same thing, just electromagnetic fields creating each other over and over as they propagate. When you turn on a light, you're creating oscillating electromagnetic fields. The electrons in the filament are being shaken back and forth by the AC current, and that shaking creates fields that propagate outward at the speed of light. And when those fields hit the electrons in your retina, they shake those electrons, and that shaking is converted into a chemical signal, and that signal travels to your brain, and somehow you experience it as light. All of it is electromagnetic fields, all the way through. The current in the bulb creates fields. The fields propagate through space. The fields interact with charges in your eye. Different frequencies of field oscillation are perceived as different colors. And here's the beautiful part. The speed of those waves, the speed of light, that's not an accident. It's determined by two numbers: the permittivity of free space and the permeability of free space. One measures how strong an electric field you get from a given charge. The other measures how strong a magnetic field you get from a given current. Maxwell took these two numbers, both measured in static experiments, experiments where nothing was moving, and he combined them mathematically, and out popped the speed of light. Exactly. That's when he knew. Light is an electromagnetic wave, moving electric and magnetic fields. That's all it is. Nobody expected that. Nobody was looking for a connection between electricity and light, but the math insisted, and the math was right. Now let me tell you about power transmission, because this is where people get really confused. You've got a power plant generating electricity. It needs to get to your house, maybe hundreds of miles away. How do you send it? Most people think you just run a wire and push electricity through it, but there's a problem: resistance. Every wire has resistance. And when current flows through resistance, you lose energy as heat. For a long wire carrying lots of current, the losses would be enormous. Most of the energy would heat the wire instead of reaching your house. So how do we solve this? We use transformers. We step up the voltage, way up, hundreds of thousands of volts. And here's the trick. Power is voltage times current. If you increase the voltage by a factor of 1,000, you can decrease the current by a factor of 1,000 and transmit the same power. And resistive losses depend on current squared. If you cut the current to 1,000th, the losses drop to 1,000,000. Suddenly, those long transmission lines become practical. Then near your house, we step the voltage back down to something safe: 120 volts or 240 volts. The current goes up again, but now it's only traveling a short distance, so the losses are acceptable. The whole system works because we can manipulate voltage and current independently. We can trade one for the other, and that's only possible because we're using AC, alternating current. With DC, with direct current, you can't easily change voltage. There's no simple transformer. Every voltage requires a different generator or a complicated electronic converter. That's why Edison lost the war of the currents. DC doesn't scale. But AC, because the fields are oscillating, you can use electromagnetic induction. A changing magnetic field in one coil creates a voltage in another coil. The ratio of voltages depends on the ratio of turns in the coils. Simple, elegant, efficient. And it's all because of Faraday's law. A changing magnetic field creates an electric field. That's it. That's the principle that powers civilization. Now, here's something that really bothers people when they first hear it. The current going into your house is the same current coming out, exactly the same. Every electron that enters leaves. The number is perfectly balanced every instant. People find this confusing because they think your appliances are consuming electricity. They're using it up, but they're not. They can't be. Charge is conserved. Electrons can't be created or destroyed by plugging in your refrigerator. What your appliances consume is energy, not charge. The electrons flow in, they give up energy to the appliance, and they flow back out. They're just carriers. They deliver energy and then leave. It's like a conveyor belt. The belt goes in a loop. It carries packages from one place to another. The packages get removed, but the belt keeps going. The belt itself isn't consumed. Same with electricity. The charges go in a loop. They carry energy from the power plant to your appliance. The energy gets removed, converted into light or heat or motion, but the charges keep going. They flow back to the power plant through the return wire. And actually, it's even stranger than that. In AC power, the electrons aren't even making the round trip. They're just vibrating in place. The energy is being delivered by the fields, not by the motion of the charges. The electrons are just markers. They're just there to show where the fields are and how strong they are. The real story is the electromagnetic field configuration and how it carries energy from place to place. Let me tell you about grounding, because this is another source of confusion. People think the ground wire is there to carry current, that if something goes wrong, the current flows into the ground and disappears. But current doesn't disappear. It can't. Every current flows in a loop, always. So what's the ground wire actually doing? The ground wire is there to provide a low resistance path to Earth for fault currents, not normal operating currents, fault currents. Currents that flow when something breaks. Imagine a toaster. Normally, current flows from the hot wire through the heating element and back through the neutral wire, a complete loop. The metal case of the toaster is just sitting there, not part of the circuit. But suppose the insulation on the hot wire breaks and that wire touches the metal case. Now the case is at 120 volts relative to ground, and if you touch it while you're standing on the floor, you complete a circuit. Current flows from the case, through you, through the floor, through the earth, back to the electrical panel, and returns through the ground connection at the power plant. That current through you is enough to kill you, not because it's a large current in absolute terms, but because it's enough to disrupt your heart. The ground wire prevents this. It connects the case directly to Earth with a very low resistance path, much lower than the resistance through your body. So if the hot wire touches the case, current flows through the ground wire instead of waiting for you to touch it. And that large fault current trips the breaker, shutting off power to the toaster before anyone gets hurt. But here's the thing. Under normal operation, no current flows through the ground wire. None. It's just sitting there waiting. It's insurance. It only carries current when something has already gone wrong. And the Earth itself isn't a magic sink for current. The current flows through the Earth back to the power source. It's still a complete loop. The Earth is just a very large, very low resistance conductor that we use as a common reference point. Now let me tell you something about superconductors, because this is where our intuition about electricity really breaks down. In a normal conductor, electrons drift slowly through the material, scattering off imperfections, losing energy as heat. There's always resistance, always some loss. But in a superconductor, cooled below a critical temperature, the resistance vanishes completely. Not just very small, actually zero. You can start a current flowing in a superconducting loop, and it will keep flowing forever, literally forever. We've set up superconducting loops and measured them years later. The current hasn't decreased, not even a tiny bit. This seems impossible. Where does the energy come from to keep the current going? But that's the wrong question. The current doesn't need energy to keep going. It only needs energy to get started. Once it's flowing, it just keeps flowing because there's nothing to stop it, no resistance to slow it down. It's like a satellite orbiting Earth. It's not using fuel to stay in orbit. Orbit is the natural state. It would take energy to stop it, not to keep it going. Same with current in a superconductor. Flow is the natural state. And this happens because of quantum mechanics. The electrons aren't behaving as individual particles anymore. They're forming pairs, Cooper pairs, and these pairs all move together in one coherent quantum state. You can't scatter just one electron because it's not just one electron anymore. It's entangled with all the others. They're all moving as one object. And to scatter that object, you'd have to give it enough energy to break up the pairing. Below the critical temperature, thermal vibrations aren't strong enough to do that. So nothing scatters. No scattering means no resistance. This is genuinely quantum mechanical behavior on a macroscopic scale. You can see it. You can measure it. Quantum mechanics isn't just for atoms anymore. And superconductors do other strange things. They expel magnetic fields. If you put a superconductor in a magnetic field and cool it below the critical temperature, the field gets pushed out. The superconductor becomes perfectly diamagnetic. Why? Because any magnetic field inside would induce currents in the superconductor. And those currents, since there's no resistance, would flow until they created a field that exactly cancels the external field. The inside of a superconductor is a magnetic field-free zone. You can levitate a magnet above a superconductor. The induced currents create a field that pushes back perfectly. No friction, no losses. The magnet just floats there. This is real. This is how nature actually works when you get things cold enough. And we have no intuition for it because we don't live in a world of zero resistance. We live in a world where friction and resistance are everywhere. But at the microscopic level, at the quantum level, resistance isn't fundamental. It's an emergent property. It's what happens when quantum coherence breaks down and you get scattering. Take away the thermal vibrations, maintain the quantum coherence, and resistance vanishes. So what have we learned? Electricity isn't what you thought it was. The energy flows in the fields, not the wires. The electrons barely move. Voltage is always relative. Current always flows in loops, and none of it makes sense without quantum mechanics. And every time you flip a switch, you're manipulating quantum fields on a macroscopic scale. You're creating disturbances in the electromagnetic field that propagate at the speed of light. You're converting energy from one form to another using principles that weren't even discovered until the late 1800s. And somehow, despite all this strangeness, it works. We can calculate what will happen. We can design circuits. We can transmit power across continents. We can communicate instantly across the world. Not because we understand everything. We don't. We don't know what charge really is deep down. We don't know why quantum mechanics works the way it does. We don't know why the universe has this particular set of field equations instead of some other set. But we know the patterns. We know what happens when you do this or that. We can predict, we can build, we can use it. And that's physics, not knowing everything, not having all the answers, just having enough understanding to see the patterns and work with them. The universe is under no obligation to make sense to us. It does what it does. Our job is to figure out the rules, and the rules of electricity, of electromagnetism, are strange and beautiful and completely non-intuitive, but they're real. And every time you turn on a light, they're working exactly as they should. The fields propagate, the energy flows, the electrons jiggle, and somehow, out of all that quantum mechanical strangeness, you get light. That's electricity, not what you learned in school, what it actually is.